Next up, we've got Tyler Morgan-Wall. Tyler is a research staff member at IDA, and he's the developer of the Skipper software library that many of us know and love, which is its library for power analysis and design generation. And he's also authored lots of other R packages for mapping, cartography, and so on. Tyler also has a PhD in physics from Johns Hopkins, and he lives in Silver Spring. Please welcome Dr. Morgan-Wall.
All right, great. Yes, thank you for the introduction. Yes, I'm Tyler Morgan-Wall. I'm a research staff member here at IDA, and I'm going to be talking about a methodological improvement that we've developed here at IDA, optimal transport-based space-filling designs for AI-enabled and autonomous systems. So as a quick overview for this talk, first I'm going to discuss what was the motivation behind it, why this work matters. Then I'm going to give a quick introduction to space-filling designs and the field of optimal transport, just enough to cover what our new method is. And then I'm going to go over the comparison between existing space-filling design methods and our new method, and then give some conclusions and some implications for T&E. So to begin, what problem are we trying to solve? So we've entered the era of AI and autonomous systems. And as part of that, we now face a huge increase in the complexity of the systems that we are tasked to evaluate. And with traditional systems, a lot of the uncertainty comes from the actual performance of the system itself. The system itself was deliberately engineered, and it is employed by trained operators. But when we move to, let's say, autonomous systems, we lose the trained operator piece. So suddenly the system doesn't only have to accomplish its mission, but it also has to understand the environment it is in order to then accomplish that mission. And that brings with it a huge increase in complexity. And AI removes the deliberately engineered piece. No longer do we have software engineers and SMEs designing the system. We now have a bunch of training data and a very adaptive neural network that are combined to then learn how to accomplish the mission. And the issue with that is that these AI models tend to fail in ways that are very unexpected. So all of this combines to say that we face the issue of having to test these extremely complex systems with our very limited budget of time and money. So how do we do that? Well, one way to potentially do that is to use simulation. And in fact, we do this with many non-AI and autonomous systems now because our systems are getting very complex. So we use some form of simulation to then test our systems. A way to do this and still actually use live testing, because we still want to test the system in real life, is to use your live test events to VVNA. So use that as sort of the gold standard data that you then use to VVNA your simulator, which you then use to run a much larger runs for the record test campaign, which you then use the output of those results to to develop a statistical model, which you then use to densely evaluate the system across the entire space, which you then use to develop your report, and then deliver your findings to the operator, your customer, or whatever. So the important point is this. This simulator piece is critical because while this is cheaper than live testing, otherwise you wouldn't do it, it is not cheap. Simulator testing can take months of time to run, large server farms, lots of GPUs, potentially. You can have lots of manpower requirements. This can result in a significant schedule shift right for actually getting some capability out to the operator. And so if we were able to make this design better, maybe we could make these designs smaller and thus deliver capabilities faster and more high quality results in our report. So why don't we just use traditional DOE? Traditional DOE is really optimized to extract data when you have a noisy response. And in this case, we have, for computer-based experiments, we have a deterministic response in that you have the exact same inputs, gives you the exact same outputs. And traditional DOE is not optimized for that case. In fact, things like replications, blocked factors, randomization, these are meaningless for computer-based experiments. They don't give you anything. methodology like response surface methodology, which does allow you to sort of explore the space, is good for finding like optimal conditions for where your performance is best. But we want to understand where the performance is best as well as where the performance is bad. We want to characterize the full space. So what drives uncertainty in M&S is the sampling density. So your uncertainty at the points that you measured in your simulator is 0. Where you do have uncertainty are the spaces between your samples. And in fact, you can see that for a squared Gaussian kernel, that this uncertainty grows as the distance to the nearest point squared. So a good design should minimize the size, the distance to any one point, basically should minimize the size of any voids within your design. And that's what leads us to space-filling designs. Space-filling designs minimize this uncertainty in predictive performance by filling the space evenly. So on the left, you can see two plots here. On the left is a 1D design where we have evenly put the points throughout the space, whereas on the right, we have unevenly put them or distributed them through the space. And you can see that the blue, which represents the uncertainty in the predicted performance, grows very quickly for that particular example and actually encompasses the red dotted line, which in this case represents some sort of hypothetical threshold. So the report for the left-hand side, we would be able to say, yes, this system falls underneath and is effective across the entire operational space, whereas in the right side, where we just have a worse design, same number of points, we would not be able to report that to the operator. It would be a watered-down, less useful report. So this is why design quality matters when it comes to these simulated, or these computer-based experiments. So hopefully that sort of motivated why space-filling designs are useful, why we want them, why we want to improve them. And in fact, I'm not the first person to have this idea to, hey, let's tackle space-filling designs. There's been many different attempts to create a really good algorithm for doing this. Some of these have used physical analogies, sort of like electric charges to distribute points throughout the space. So a lot of them just take all of the pairwise distances and try to optimize them. Fast flexible filling is nice. They use a clustering-based approach. But a lot of these algorithms have some downsides. And limitations. Specifically, most of these have limited support for disallowed combinations, with the exception of fast flexible filling and a little bit of the energy-based one. The few have support for categorical factors, and all of them, with the exception of LHS, which doesn't have a very good space-filling properties to begin with, they all have poor, which is to say greater than linear computational complexity. Every point you add to a design is more expensive than the last point. And that is because all of these existing space-filling designs, algorithms, in some way optimize some function of the distance matrix, which is a square matrix that basically represents all of the pairwise distances between each point. Being a square matrix, this thing grows as n squared. Every point you add, you have to compute all of the previous distances to that point. And because of that, most of these algorithms grow by n squared. With the exception of fast flexible filling, it's a pretty good algorithm. It's somewhere in between, a little less than quadratic, because they use clustering, and there's some benefits from that. But the issue, though, with all these algorithms, or most of these algorithms, is deeper than that of computational complexity. The issue is that these sort of self-assembling structures where you actually reference the other points to then try to get to an optimal configuration is not, you don't want to push yourself away from a bad configuration, because that's very unlikely to lead you to an optimal configuration. What you instead want to do is pull yourself towards a known good distribution. When you have a marching band, they don't reference other people around them to form these pictures. They look down and they know where to go on the field. They have a grid. They have something ideal that they reference and learn and go to that. And the issue with methods that try to just push away from bad areas is it's also more of a high-level philosophical thing. It's hard to just go away from a bad situation and end up in a good situation. Well, the same thing is for these algorithms. So what we want to do is we want to tackle the space-filling design problem without using the distance matrix. And how we can do that is, let's say we have some, so that red represents some ideal uniform distribution, and we have those black points, and we want to distribute them some way that's as close as possible to the underlying uniform distribution. So on the top one, that would be a worse or further away from what we want to do, and the bottom one would be closer. And so what we want to see if there's any sort of way to measure how far a distribution of points is from another distribution. And that is provided by the field of optimal transport, which it solves or is a field that is concerned with solving the Monge-Kantorovich transportation problem, which is basically just the most cost-efficient way in terms of some mathematical cost function of transporting one distribution of mass to another place. And when you find that optimal way of transitioning, of moving that distribution, that's called the optimal transport plan. OT plan, which is a very confusing term for this this talk, but I'll refer to it as the optimal transport plan to be clear. So this has tackled issues like, let's say you have a bunch of steel mines and you have a bunch of steel factories, and you want to be able to determine the best way to get, given that each mine produces a different amount of steel and each factory produces a different amount of factory, the best way to transport that over geographic distances. That was the kind of a problem that this was originally tackled to solve. So this field of mathematical study gave us something called the Wasserstein distance, which is this equation up here, which is just the cost of moving all of those points, the total cumulative cost of moving all these points. This equation looks pretty, maybe a little intimidating, but all it's saying is sum up all of the distances. In fact, we can see here, I have an animation of this distribution of points, which represents the letter A, transforming to a distribution of points, which represents the letter B. And the optimal, the Wasserstein distance is just summing up all of these little distances squared for this case. So that's all that represents. You take the beginning place, the end place, and you square all the distances and you sum them up. That's what that quantity represents. The issue with this, though, is you can see shift 2 points, make 2 different decisions. This is actually intractable when in large dimensions with large numbers of points, because there's so many different ways that you can swap two different points. So to give you a more concrete example for what we're talking about, so let's say you come back from DataWorks and you got a great little new tchotchke for your bookshelf. So you decide you need to move over your books. So you take it. There's 2 ways you can do this. You can either move the red book from the beginning to the end, or you can move each book individually 1 to make room for the bookend. So if you have a cost function where you're using the distance squared, so p is equal to 2 in the Wasserstein distance formula, you can see that you'll have a total cost of 9. Whereas if you have move each one individually 1 unit over, that is a total cost of 4. So that would be the optimal transport plan for solving this particular problem. And in fact, in this 1D case, the optimal transport plan has a closed form solution. And what you do is you just simply sort all of the points along your line. You sort from your source distribution. You sort them along your line in your target distribution, and you just match them up. First point to first point, second point to second point, third point to third point. And the distances between each one of those, all of them together, make up your optimal transport plan. So it's pretty straightforward in 1D. In 2D and 3D and ND, though, you can't do this. But you can actually use the idea that you can solve this in 1D to form an approximate solution. And that's what researchers did in the early 2000s. They developed this method called sliced optimal transport, which the optimal transport problem is very hard. But what you can do is you can just take a 1D slice through whatever n-dimensional space you have and project those points to that and sort them along that line. And you can take another slice and you can sort them along that line and another slice. And you can do this tens, dozens, hundreds, thousands of times. And what you actually end up doing through all those samples is estimating what the optimal transport plan is at that point. And this is a Monte Carlo method for solving this problem. And the great thing about this method is you're not using a distance matrix. You're not actually comparing points at all. You are just sorting. And computers are very good at sorting. So here I have an animation showing this algorithm in action. So the black points represent your points that you want to turn into your space-filling design. The red points represent draws from that underlying target distribution, and the arrows represent the estimate of the optimal transport plan for that point at that moment from all of those different samples. So you can see here that the points kind of move around and jiggle around, and they sort of get into a space filling configuration. But the issue here is that this is a Monte Carlo algorithm and there's noise. So what we need to do is actually just increase the number of samples. So those little transparent red dots in the back, those are additional samples. So we're taking a lot more now. And you can see here, the points very quickly arrange themselves into a very nice space filling configuration. And they sort of sit there, and we can increase the number of samples even further, and this will increase even more. So the starting configuration doesn't matter. We can see here that we have all different starting configurations, and the blue lines represent the trajectories over time, and we can see that that converges very quickly to not the same exact space filling design, but a almost equivalent space filling design. And then after a while, this very quickly converges to fill in the big voids, but then there's small shifts as it finds small improvements over time. This scales up really well because remember, we're not comparing points, so we're comparing to the underlying distribution for the uniform distribution. So we can just scale up the number of points, and this converges basically equally as quickly. And here, the fact that we have 10 times the number of points, this didn't take 10 times as long to converge. But the great thing about this method is because it actually uses draws from an underlying distribution, you're not constrained to be in a hypercube like a lot of these other algorithms constrain you to. You can draw from any distribution you want. So here I've added some linear constraints. So this would be like a flight envelope in your test. And we can see that this very quickly adapts and moves the points to that region in a space filling configuration. And this is not a box. So this is not something that would be very easy to generate using sort of closed form algorithms. But not only that, is we can weight these. So let's say on the left, I have a 2D normal distribution, and we can see these points arrange themselves according to the underlying density. So if let's say you had some sort of expected improvement criteria, or you had some prior knowledge where you knew you wanted to weight some region of your design space more than others, you could do that. Here we have on the right, you can see a ramp. So this is just a linear ramp, and we can see the points linearly increase in density over the space while maintaining that nice space filling property. So we can control the spatial distribution, but what about categorical factors? So in 2022, so graphics researchers and 3D rendering released a great extension to the sliced optimal transport method that basically included the ability to optimize many different objectives at the same time. So this allows you to, let's say, optimize. In this case, I have an image of myself pre-beard with where we're not only optimizing the spatial configuration, so the density or the intensity of the image, but also simultaneously optimizing the underlying color channels. This is a CMYK image. You can see this more clearly in this example here. You can see we have 3 classes of points, so this would be like 3 categorical factors. And here you can see the points arranging themselves to be not only have a nice global configuration where all the points are fairly well spaced apart, but if you look at the red channel individually, the blue channel individually, the green channel individually, they all are fairly well and evenly distributed. So let's do a quick test. I'm going to have you look at this for a couple seconds, decide which one you think is the most space filling, and by that I'm defining has the fewest number of voids. So take a look, vote in your head, and now here are the results. So our methods are located here in the purple in the top and the bottom. SOT with Max Pro is we do our sliced optimal transport, and then at the end we do a constrained Max Pro optimization that doesn't allow the points to move a lot, but just a little bit, and that actually provides some nice benefits to uniformity. So those are our 2 variants, and you'll see those listed in the slides when we do our comparisons. But that was just a visual comparison, and it's very hard to do that in dimensions greater than 2 because when it's very hard to imagine 4D space. I can't do it. I don't think many people can. But generally, you need to have more of an empirical way of studying this. So what I did to do this, there's a couple of different ways. So a standard way in space filling design research literature is to look at distance metrics, which is to say you look at the distribution of points and you look at what is the minimum distance between any 2 points. Because if you have 2 points that are too close together, that likely means that there is a large void somewhere else, or average, there's too much of a void between points than there should be. We also can assess design quality by looking at the predictive performance. So by looking at the average root mean squared error, as well as what the maximum predictive uncertainty is. So that's that blue on that rainbow plot where we saw the big blue uncertainty intervals. That's minimizing whatever that maximum value is. Because as we see, that could be, when you have a very large maximum uncertainty, that could really water down the conclusions that you can make. And then finally, we also look at generation time. So how well does this thing scale computationally? And so we have a lot of different design sizes we've looked at in this study, multiple independent generations per design, and then many different evaluations for each one of those designs. So here's the first set of results. So here you can see it's a histogram of the various minimum distances. So point-wise, whatever 2 closest points were close together in each design. So there's one measurement per each design for this. And we can see our purple and pink designs, the sliced optimal transport ones, are by far in a class of their own. So greater is better. So here we have different design sizes. So that starts with 60 runs down to 200, and then the growing here is the x-axis represents a larger minimum distance, which is a more desirable property. So we can see here that in the black line, dotted line represents sort of the average theoretical, given that density of points, you can compute sort of an average value for what that density should be. And not only does our design consistently beat all of the other designs in terms of minimum distance, it also consistently beats the average. And it does this for all of the different design sizes we saw here. So this is the 5D case. We also can look at the 8-dimensional case. And again, exact same story. All of the other designs tend to cluster around the average. Ours consistently beats it. You don't need a statistical model to see that this is a significant difference. However, distance metrics, while they're a great proxy for design quality, they don't tell you how good the design is, because we don't use designs because they have good they don't have good distance metrics. We use them because they have good predictive ability, because that's what we end up are doing with this. So what we actually want to do, and what I did in the second half of this analysis, is to actually see how well these things can predict some arbitrary function or some function, and then measure that error in prediction and measure how large the uncertainty grows. So here, the purple, let's say we have some test function. We use our space filling design to fit a model. So then we use that to get that purple function. And then we draw a bunch more samples from that test function and then see what that error is. So that's one. That's the average root mean squared error. We looked at that. But we also want to look at whatever that maximum uncertainty is. One point about this is for analyzing this particular metric, it's actually kind of hard because how well a space filling design does is actually related to how well not the overall design quality is, but if it managed to sample the one place in the design that shifts very quickly, because the area where the function is changing quickly is the area where you want to have samples. So it's actually very hard unless you generate a bunch of independent designs for everyone to kind of, some designs will just get lucky and manage to sample that point. But you can kind of get around this because when you take a uniform design and let's say you swap some axes or you rotate it or you flip it, there's a series of transformations you can do that leave you with a uniform design. So by applying a bunch of transformations where we flip and swap axes, and then end up with a different configuration, but effectively for that test function, an independent look at that the root mean squared error. That allows us to kind of get a better look without generating thousands of these designs, while still minimizing the effect of just some designs getting lucky. So there's two test functions, not much to say about these other than they're pretty standard in space filling design research. The most important thing is that they're kind of nonlinear, so they're hard to fit. We are choosing designs with greater than 10 times the number of points or 10 times the number of dimensions. And that's because multiple papers have shown that designs with fewer runs than that, they're not really space filling at all, and they just have really unpredictable performance. So here's the first set of major results from this. So this is looking at the average prediction performance, and we can see that, so the pink and purple is ours, and we see that it by far does the best across, and the performance gets better as the design size grows. The model just shows that we are, very statistically significantly better than all the other designs. And this corresponds to about an 8% improvement in average predictive performance, which is compared to the current state of the art, which is fast, flexible filling. So that's a great result if we want to say, hey, this is we'll give you better predictions, because we can see this here, and so lower in this case, the y-axis is the average prediction variance, and lower is better, because we want to have a lower root mean squared error. So for the maximum model uncertainty, which is that sort of blue, measures sort of the voids, we see that the sliced optimal transport method blows the rest of the space filling design methods kind of out of the water. We see actually a 25% improvement from compared to fast flexible filling. And that makes sense because you can see in the image how well this method managed to fill in those voids, and this maximum uncertainty is related to the size of these voids. So the fact that we have really good distance metrics, this corresponds to a great win for this maximum predictive uncertainty. And in fact, this 25% improvement is huge because it corresponds to, let's say, if you were using this to size your test, to a 25% reduction in the number of resources or time you would need to achieve the same maximum predictive uncertainty. So you could potentially turn a 4-month test into a 3-month test. That is how significant that 25% is if you were using maximum uncertainty to size your test. However, so nothing can be perfect. In 8 dimensions, I saw a really weird behavior, and it took me a little while to figure this out. But it turns out in 8 dimensions, high dimensional spaces are a little weird in that most of the volume is actually in the corners. It's weird, but that means that when sliced optimal transport tends to put points into basically the biggest voids, for the first, when you haven't yet filled in all the corners, so for 8-dimensional spaces, you have a box with 256 corners, it'll just tend to put points in that corner. So it's not filling the interior of the space yet. So below that 256 value, it's really not space filling. So that's the one limitation for this algorithm that I found so far, is that you really need to have greater than 2 to the d, where d is the dimension number of points, in order for it to be truly space filling. And in fact, when we look at designs greater than 256 for this case, we see that we no longer see that weird, unpredictable behavior, which is just because we're not sampling the full space. So there are areas where the function is moving very quickly that we're not capturing, so we get a large error in those cases. Now we are capturing it in the interior, so then we get recover about equal performance, slightly better, but not statistically significantly to fast flexible filling. However, because those voids are related to the maximum uncertainty, when you have a void at the corner, you're going to have a high uncertainty there when you want to predict what the resulting performance is there. We actually do see still good performance when it comes to maximum model uncertainty. So here we see we are still substantially better than the current state of the art and all of the other algorithms. And then we look at the larger designs, we see the same thing, about 8 to 15% improvement, 15% greater when we filled up the box. So we see a really, particularly for this question of maximum uncertainty. So if you want to minimize your uncertainty, regardless of the dimensionality or number of points, we see that sliced optimal transport, this method, really does great. So finally, I'll talk a little about, this is the only slide for this, the computational complexity. So what I fit here was simply, this is a log-log plot. So it's measuring the time versus the number of points. And from a log-log plot, we can extract the exponent from if we have some sort of exponent dependence from the slope of that line. So a better algorithm is going to have a lower slope. And we can see that the sliced optimal transport by far has the slowest slope, which is about 1, which is great because it means that every point is about equally expensive to add to the design as the previous one. Whereas Maximin, Max Pro, and Uniform all have greater than quadratic, which means you're limited to designs of a few thousand. And fast flexible filling has kind of splits the difference because they have this nice clustering, which sort of gets you a little gain in computational complexity. But even then, that limits you because each point will be more expensive than the last. So this really is the key point for when it comes to AI and autonomous systems, because when you have these very complex systems, what happens is you are going to have to produce very large designs eventually. And with that, we don't want to run into the situation where none of the methods we have can actually support that kind of design. So finally, conclusion, we've introduced a new method that we're going to be hopefully releasing a paper out on soon, as well as some R packages, so you could do this at your organization that is both highly scalable and highly adaptive towards all of the complex test design scenarios that we encounter for AI and autonomous systems, but also for non-AI systems that just need large tests. So these methods, not only we've shown can seem to exceed the current best state of the art, but also seem to bring all of the great quantities of having lots of flexibility and hopefully can end up delivering capabilities faster, as well as reducing test costs and shifting schedules left to make this simulation part of the test campaign and OT and DT testing more efficient and provide better results to the operator. So thank you.
All right, well, you have tried to crowd out all of the questions, but we'll do at least one virtually. From Kevin, he asked, do the slices have to have any particular properties other than being unique? Is there some sort of well-conditioning criteria to select the slices?
No, it's just a random vector. If you have n dimensions, you choose n-dimensional vector. And then you just say, it should be, if you more evenly sample throughout the space, you will get a better estimate of the optimal transport plane at that point. But really, at that point, it's more just about computational efficiency. To make this work, you don't have to have any particular arrangement other than it should be uniform. It shouldn't be biased in any way.
Thank you.
All right, great. Thank you so much.